Hello and welcome. My name is Stephen Ethridge. We're down here at the wonderful Gustafson Brothers Training Center in Huntington Beach. It's Sunday, the September 19th, and we're enjoying some great weather with my good friend Steve Caruso. Basically what we're going to do today is we're going to take a look at 5-gas at a 6th grade level. And what I'm going to try to show you are some rudimentary concepts, but I think that they're foundational in being able to diagnose and repair smog failures and also understand the combustion process and the after-treatment process that are provided on today's automobiles. This is what we're going to be working with as far as an outline. The things that we have to recognize today is that we're going to be talking about some terms that are a little bit different. We're going to be talking about terms like oxidation and reduction and how they affect the process of applying after treatment to an exhaust gas. And we're going to be talking about what we get in versus what we got out. Now, there's no way in the world that you're going to get something out of something that you didn't put into it. In the case of an automobile or internal combustion engine, there's a couple of things that you need to recognize. Number one, if you're building a campfire, the triangle of fire is all you really need. You need a little heat, you're going to throw a match in, you're going to have some oxygen, some fuel, and you're going to make a really, really nice campfire. But if you have to drive out of your campsite, you're going to need a running engine. This is going to be a little bit different because it has another thing that's involved in it. You've got fuel and air, sure, hydrocarbons and oxygen. You've got ignition. This is still consistent with what we had going on. But we just changed from a triangle to a quadrangle. Now you're going to need compression in order to extract the energy out of that combustion event. In order to do so, we're going to talk a little bit about what goes into the engine. Well, you're going to have air. It's about 21% oxygen and about 79% nitrogen. Now, oxygen is important for oxidizing carbon and hydrogen in order to create a heat building event. And you're also going to have fuel. This is hydrogen and carbon. You guys recognize it as HC if you're looking at a 5-gas analyzer. You're going to put that nitrogen, oxygen, hydrogen, and carbon and introduce it into the intake manifold, or in GDI configuration, you'll have an actual injector in the combustion chamber. From here, you're going to have a chemical reaction. Now, all chemical reactions have a byproduct. Whenever you change the chemical state of a particular molecule, you're going to actually have something else given off of it. In this case, we're talking about heat. Some cases you can have light. You're striking a match and causing it to burn. You're going to get heat and light energy along with those original properties that you're introduced into the fire, the fuel and the oxygen. But in this case, we're going to introduce the hydrogen, carbon, nitrogen, and an O2 into the intake manifold and put it through a stress event. So the stress event is where the piston comes up and we're going to generate a little bit of heat. Again, we needed heat in both cases, but we're also going to add an ignition event. So you're building the heat as the pressures come up, and then the ignition event triggers the expansion of gases and the oxidation of the hydrogen and the carbon. They're going to combine with oxygen and they're going to create heat. Now, the reason why we have nitrogen in there is not only because it's part of our atmosphere and it has to come along with the oxygen, but also nitrogen is highly reactive to temperature changes. So when you heat up the nitrogen, which is about 79, 80%, it's going to expand a great deal. It's going to take up more space. As it takes up that more space, the pressure increases. As the pressure increases, now we've got a force to push that piston down and translate that energy into the crankshaft and make your wheels move, and you can drive away from your campfire. From there, this little dance takes place. So you've got the combustion event occurring and you're changing partners. So you've got oxygen and nitrogen and carbon and hydrogen all in the combustion chamber. They're creating heat, and oxygen, hydrogen, and carbon are all going to start to combine. Now, you're not getting anything out of here that you didn't put into here, but there is a change in form. So the change in form, depending on what the temperature is inside the combustion chamber and how high the pressure is, can also form another molecule that doesn't like to join together. We've got 20% oxygen, 21% oxygen, and nitrogen, about 79 to 80% in our atmosphere, but it never joins into NOx. But inside the combustion chamber, we have an environment that is special. The temperature, if it gets over 2,500 degrees, which can come from a poor cooling system to too far advanced timing, any of a number of things can conflict as carbon buildup in the cylinder. You can get the temperature inside the cylinder to over 2,500 degrees, or the pressures to be very, very high, and that also increases the temperature, and you can get a strange gas, which is NOx. From here, we've got the CO2, which is a good gas. The CO2 is the oxygen and carbon that combined in complete combustion. CO2, we want to see about 15%. We want to see it very, very high. We're also going to have some H2O, some water vapor. You're going to make about a gallon of water vapor for every gallon of fuel you burn. And this is all good gases, CO2, H2O. H2O is not measured, but this is what you're going to manufacture with complete combustion. Now you've also got trace elements in complete combustion of hydrocarbons, CO, O2. Those are going to get in here and they're going to be picked up by the catalytic converter, which we'll be back to in a second. In the event that you've got temperatures that exceed 2,500 degrees, you're going to have a small amount of NOx anyway. But if the cooling system goes south, the compression gets too high, the timing's too far advanced, and you have a number of things that cause the combustion chamber temperature to rise above the threshold level of 2,500 degrees, you're going to have an excessive amount of NOx. Now, if you notice that the C, the O, the H, the N are all right here. O, N, H, C. What are you getting out? O, H, C, N. Now usually the nitrogen will pass straight through and not have a problem, but you're going to have complete combustion or not desired gases. If you take a look at the air-fuel ratio chart and you take a look at your 5-gas analysis, you can take a look at 2 gases and identify whether or not you have gotten to the point where you're running rich or lean. If you get down to 10.0 to 1, a rich mixture, you're going to have high CO. And you can see on the graph as you go leaner and leaner, the CO goes away with complete combustion. And you can see the O2, if you're very, very rich, all the oxygen would have been consumed. But as you get to the point where you're at stoichiometric, both of these gases cross at a point. From there, you go very, very lean as you get leaner and leaner, which means that you had plenty of oxygen but not enough fuel. In this case, you've got plenty of fuel but not enough oxygen. So if you take a look at CO and O2, you'll identify very, very quickly by whichever one is higher, where you're running in the rich lean condition. If they're both about the same, you're in good shape. Now, some of the things that we need to know about CO2, your CO2 is going to drop with any inefficiency. So the CO2 is going to drop in the toilet. But these chemicals have to go someplace. Carbon and oxygen still have to go someplace. So in the event that we've got a point where the HC comes in and goes out the same way, if you've got hydrogen and carbon that is high, you missed the fire. For whatever reason, whether a lean misfire or an ignition misfire, lack of compression, and again, we're back to that compression word. You need to have compression in order for an internal combustion engine to operate. And the gasoline, it needs it to be able to derive power. And the diesel, it needs it to that provides the actual ignition. So if you've got high HC, you missed the fire. If you got high CO, you ran out of air. If you've got more than about 0.3%, 0.3%, you're lean or you ran out of fuel. If it's much higher than that and the HCs are up, you've got a misfire. If you've got temperatures over 2,500 degrees, you're going to have high pressure in the combustion chamber, carbon buildup, timing too far advanced. Even low-grade fuel can create a situation where the NOx goes incredibly high. Inside the catalytic converter, which is our after-treatment process, we have two beds. One is reduction, one is oxidation. Now, anytime we're talking about reduction, we're talking about NOx. This is where I'm going to reduce NO to the X to something else. So in this particular case, I'm going to reduce NO to the X. I'm going to take away the O to the X. And I'm going to let the N run right on through. So the nitrogen is going to continue through, but I'm going to hold on to the oxygen. Now the cool thing about the reduction bed is it also works as a oxidation bed. So the oxygen that's being held in the reduction bed, when the HC and CO come through, it allows that oxygen to grab a hold of the carbon and the hydrogen and become CO2. Bonus. The rest of it is all going to move through. We've got CO2 coming through, and any oxygen that made it through the reduction bed is now being held by the oxidation bed. The oxidation bed, if you remember the early days, before three-way cats, we had catalytic converters, and it only had one bed in it. It was there to reduce HC and CO. The way that it went to reduce HC and CO is they called it an oxidation catalyst. So it added oxygen to the HC and CO and turned it into H2O and CO2. So in the early years, we had just the oxidation cat. So as we add oxidation to it, we end up with tailpipe gases. And what we want to come out of here with is CO2, H2O, and trace amounts of O2. That should be our end game for the catalytic converter. As you're watching the catalytic converter, it's important to recognize that post-cat O2 sensors did not have any stipulations and regulation for the post-cat O2 to be monitored. So if you've got an earlier than 2005 car, the post-cat O2 can play a real wild card in what you're trying to do to diagnose this thing. It was, on the other hand, responsible for what they called final fuel trim, but that's another story for another day. If you're taking a look at the O2 sensors in a healthy combustion condition, you're going to see oscillation from about 175 to 800 millivolts. Out of the pre-cat O2, you may have as many as 10 vents where it translates across the 450 millivolt midpoint of the scale in a second, if they're really, really healthy. And then the post-cat O2 is going to give you a dithering experience where it's hovering around 500, 600, 450, but it's dithering. The dithering term is just gently cruising, and in my mind it's like watching a fella that's had too much to drink walk down the sidewalk. He's not quite going in a straight line, and your friends in law enforcement look for this in your driving habits as well, so be careful out there. At any rate, so this is your post-cat O2, this is your pre-cat O2. Remember that if your post-cat O2 is tanked, it's going to give a final fuel trim command to make this rich. And you're not going to like it. So pay close attention to the post-cat O2, get it on your digital storage oscilloscope, make sure that you've got accurate signals coming through. I hope this has been a resource that you'll rely on, and I hope that it has been positive for you. Have a great day.